The purpose of this session then on Thursday afternoon, or whenever you're reading this, is to pick up from what we did on Monday on standardized work, and I'm going to introduce you to 3 charts and an exercise for you to do by yourself. I'm just going to quickly move through the slides that we covered on Monday about standardized work so that I can get through to the session that I want to give you now. Okay, we were looking at tack time, the idea of a drum beat in which all work has to be performed before we move on to the next item to produce, and how the cycle time, the actual time we take, is generally shorter than tack time because we're not perfect, and so we have to make allowances for inefficiencies. Also how the true value-adding time is a small part of the cycle time and hence a small part of the tact. We talked about work sequence and the idea that work is done in a sequence and has to be for various product related reasons, for assembly planning and to meet various assembly constraints. Historically this has been done with diagrams like these ASME process charts, and we still use those widely today, and there's the value adding time, which is only a small part, and how we also need to introduce some elements related to ergonomics to do with body posture and so forth, so that we're not overstraining the workers. And here are Thurbligs, which has some pictograms that were used in the early part of the 20th century and can be relinked to work study data to create synthetic times for the work. Now, one of the things that Lean requires a lot of, or certainly some ability to do, is to have flexible working, meaning that people can be reallocated tasks, and this doesn't have to go through a lot of negotiation and pay bargaining and so forth, which is something that used to happen a lot and still happens in some industries due to union pressure and the division of labour. It works against us in this case. Fortunately, the power of unions has to some extent diminished, certainly in the UK. So we want to avoid the waste of waiting. We want workers to be doing useful things, and we don't want them to be tied to machines, just watching the machines work. So we want to say no to conventional machine minding. The first of the charts I want to introduce is the standard work combination table, which includes an area that describes the sequence of activities and some timing data associated with them, and a pictorial representation of the operations and the operator's movement between the operations within a certain tack time, shown by this red line here. That's the tack time. And we want to then balance the work that one or more operator, or more than one operator, does in a work cell. A work cell occurs where we have more than one person working on a sequence of tasks because we need that to actually do the work within tact. If we had just one operator, they wouldn't be able to complete all the work within the tact time. So here's a work combination table. You'll notice at the right hand edge here we've got the tack time, which has been calculated from this available time divided by the daily demand. In this case it's just over 3 minutes. And we've got a sequence of operations here, and this is a list of them, and they show for each of them in each row any hand time or manual time, any machine time, and then the walking time between them. So the walking time is shown with this dashed line here. So between this step, operation 1, and operation 2, we have 2 seconds of walking time between these two 1 seconds of actual manual time. Down here we've got 6 seconds of manual time, 49 seconds of machine work, so basically at this point the operator presses a button, the machine starts working by itself, and the operator can then move away. So this is where we've broken the relationship between the operator and the machine. So they're no longer minding the machine, they go on and do other tasks, including setting up another operation, which in this case runs for 160 seconds, which would take it, you can just see it there, beyond tact, and you see it wrap around at this edge here. All that has to happen is that we've got to make sure that this machine time is less than tact, and it is. It's 160 seconds, which is less than 170 seconds, and we've got this gap of time here which allows the work to be continued. So that's a work combination table. It provides us with a visibility of the sequence of work, the separation between manual and machine work, and the wasted time in walking. It's necessary because we perhaps haven't been able to lay the equipment out perfectly, and besides, equipment takes up space and it's inevitable that there will be some need for movement, but we want to minimize that where possible. And so we've got these bars recording the duration, and we can see at a glance how much of the tack time we're using. So I want to introduce you next to the work analysis chart, and this again shows this basic information here about the assembly sequence or the sequence of operations. Again, the manual walk time and the manual operation time, and we can see the track of the operator. And we see from 4 to 5, that line there is 3 seconds needed to walk from the rear door hem machine to the front outer panel, or whatever it is, front skin. Okay, it's in some kind of metal pallet here, and the operator picks it up, spends a 1 second or whatever it is, 5 to 6, spends 2 seconds walking to load it into the machine. In fact, 5 to 6, no, they don't walk, they can just turn around, there's no wasted time. 2 seconds to take it out of the bin, to pick it, 2 seconds to load it into the machine, and then 2 seconds to move to the rear outer, okay, which is a bit further away, turn around, load it into the machine, and 1 second to then move to the rear inner door, and so on. Now, these diagrams here, these charts, might be shown in some convenient place in a work cell, and we can start to see here how, by doing some 5S activity, we prepare the foundations for us standardizing the location of material and machinery, and in a later week we'll look at facilities layout design and how we go about deciding this particular physical arrangement of items within a work cell. But it allows a worker coming in under the principle of Shojinka to very quickly at a glance see what work needs to be done, what the definition of the task, the standardized task, happens to be. Likewise, management can very quickly understand and appreciate what should be happening when they come to observe it. Today we might supplement this in some industries, particularly those in which it's difficult to perform many operations and get a learning curve. For example, in aerospace, we might use some advanced 3D simulation technologies and virtual reality technologies to help demonstrate to a worker how to do the task and to adopt the various postures and where to approach the job. It can be quite complex in aerostructures, and so we might use some of these 3D simulation tools. But following the basic principles of Lean, that they need to be easily applied in the shop floor environment, a 2D sketch is often sufficient, and one shouldn't overcomplicate the application of Lean by using computer tools unless they are useful in help minimizing waste, for example the waste associated with quality defects or wasted effort. And the last of the charts is the work balance chart, in which we're seeking to make sure that workers are using as much of the available time, the takt time, on value-adding work. We don't want, with one exception, workers to be unbalanced. We want all of the workers on the whole to be doing the same amount of work. No one working harder than any other, with, as I say, one exception, which is it's rare for the work balance to perfectly match a complete multiple of the number of operators multiplied by the takt time within a cell. So what we seek to do is to expose the final operator in a cell and give them the lesser time. This is a signal to us that the work they're doing is not sufficient, not for their own benefit, but because we haven't been able to allocate them enough work, or rather that there is work that other operators are doing that we should be seeking to remove because it's not value adding, and move, for example, from 3 operators in the following chart down to 2. So let's just have a look at that chart. So here we've got an operator balance chart. Along the left hand axis is time, along the x-axis is the number of operators that we might use within a cell to perform all the work within takt, and we can see that operator 1 here is approximately 75% utilized with the tasks that have been allocated to them. We have an opportunity to allocate more tasks. More tasks need to be done because they're just not shown here yet. So for example, we might have here operator number 2, and in this case the set of tasks that they've been allocated is too much. It's too long to perform within takt, and we'd be seeking to move some tasks from operator 2 sequence across into operator 1. If we find that the tasks are too long to move here, then we either have to split them up or possibly allocate a task from some later operation and then be clever about the cell layout to allow them to actually switch from different sides of the cell, and this is something that we can solve using something called U-shaped cells that we'll look at later on in the course. Likewise, this operator here is under utilised. They're only working for less than 50% of the takt time, and this operator here and this operator here would be very upset. They're working hard while this person is doing nothing for some of the takt time. So what we want to seek to do is to balance the work, probably for the operator 1 and operator 2, probably up towards the 80 or 85% level, depending on how well maintained and reliable and effectively utilised the equipment can be. So balance 1 and 2 up at this level, and leave operator 3 exposed as a signal to us for the opportunity for Kaizen, for continuous improvement. And that's all I've got for you in terms of a presentation today, but I'd like you to look at the website and have a go at the exercise, which involves 4 operations. It's shown on the web page just underneath the presentation, 4 operations with a sequence of tasks, and I'd like you to balance those out just graphically. You can do it by hand or use Excel possibly, to just pick the times as shown pretty much here graphically, and balance the work. You might also want to look at some of the tasks and identify things that are wasteful and can perhaps be eliminated before you do the balance. And I'd be interested to know whether you can get away with, instead of 4 operators, 3 operators, or how closely you can balance to 3 operators. Anyway, that's for you to do as homework, and I'll see you on Monday. Thank you very much.